Welcome to this Maths Made Easy video on differentiating trig functions. So let's just take a look to start with at some general trig differentiation. And we can see this in the form of this table presented now. If we start with the three most basic trig functions here, so sin x, cos x and tan x. We've noticed we've got this coefficient here of k for each function. And this is to show us the behaviour when we differentiate these functions here with respect to x. So if we have, for example, sin kx here, and we differentiate that with respect to x, we obtain k cos kx there. So for example, if we have f of x equals, say, sin 3x, so sin 3x here, if we differentiate that, we obtain f prime of x, and that would give us 3 cos 3x there. Okay. For cos now, let's say we have f of x is equal to cos 4x here. Okay, so cos 4x. If we differentiate this, we obtain f prime of x here, and this result would be minus 4 sin 4x. Okay, and finally for tan x here, so let's write this as f of x is equal to tan of 2x. If we differentiate this here with respect to x, and f prime of x, using our table here, would give us 2 sec squared 2x. Okay, so those are just a few examples there, just showing the general behaviour for our trig functions when we differentiate. And we can also visualise this here if we start with sin x. So if we start with sin x here, okay, I'm going to write down the following functions here. So cos x minus sin x minus cos x. Okay, and what I just want to represent here is that, for example, if we start with sin x and we differentiate sin x, we get cos x. Okay, and if we then have cos x and we differentiate that, we get minus sin x here. And then if we differentiate minus sin x, we get minus cos x. And then finally, if we differentiate minus cos x, we get sin x. Okay, so we can see that that repeats there, giving us this cycle here between the trig functions. And we can also visualize this here by integration. So if red represents differentiation, then if we represent integration with blue here, well, if we have cos x and we integrate this, we obtain sin x here. Okay, and then if we integrate sin x, we get minus cos x. And if we integrate minus cos x here, we get minus sin x here. And finally, if we integrate minus sin x here, we end up back at cos x. Okay, so that's a nice way just to visualize the behavior of differentiating and integrating trig functions. Okay, moving on now to take a look at this example here where we're using the chain rule with trig functions. So in this case here, we've got f of x equals sine of x squared minus x plus 1. So here we need to make sure we're using the chain rule here. So if we let u here equal this expression inside the bracket, so that's x squared minus x plus 1. And then in that case, what we can say here, f of x is equal to g of u, which is equal to sine u. Okay, so in this case now, if we differentiate u here with respect to x, so therefore du by dx, that would simply give us here 2x minus 1. X squared gives us 2x, minus x gives us minus 1. And then if we differentiate sine u here with respect to u, so we're differentiating f of x here, which is differentiating g of u, so d by fx here of du gives us cos u. Okay, so if we differentiate f of x here with respect to u, we differentiate g of u, which is sine u, and that simply gives us cos u. So therefore, our final derivative here, so therefore derivative of f of x here with respect to x, simply gives us 2x minus 1, so that's 2x minus 1 here, times by cos of u here, where u, remember, is x squared minus x plus 1 there. Okay, and that gives us the solution there to this example here, where we're differentiating f of x equals sine of x squared minus x plus 1. And finally, let's take a look at this example here, where we're differentiating trig functions using first principles. So we started with f of x equals cos x. So here, if we want to differentiate this, this would simply be f prime of x. And here now, if we're using first principles, well, remember, we take the limit here as h tends to 0. And in this case here now, if our function is cos x, and that's going to be cos x plus h minus cos x, and this is all divided by h. Okay. Now here, we need to make use of our addition formula here for cosine. So as this is cosine x plus h, then what we can do here is write this as the limit as h tends to 0 of the expression here. So this is going to be cos x cos h minus sin x sin h. Okay. So that's going to be cos x cos h minus sin x sin h. Okay. We also can't forget our minus cos x here, so minus cos x. And this is all divided by h still. Okay. So here now, we need to take a look at our numerator and see if we can simplify this expression in any way. Well, here we notice we have cos x cos h minus cos x. So what I can do is I can put this minus cos x here with cos x cos h, and then we can factor a cos x out here. So what we've got still is the limit as h tends to 0 of cos x. So we're factoring this cos x out now. So that's going to be cos x, and in that case it's going to be 1. Cos h minus 1. So cos h minus 1 there. Okay, that would give us cos x times cos h, giving us cos x cos h, and then cos x times minus 1, giving us minus cos x. And finally, we've got this minus sin h here and sin x. Okay, so it doesn't matter which way we write these round here, so in that case, that's fine. And we've still got our denominator of h here. Okay. Well, in this case now, we need to use our small angle approximations. So, using small angle approximations, using our small angle approximations here, remember, for sine here, this approximates, in this case, if it's sine of h, this would be approximately h. Okay, and we also have cos of h here, so cos h would be approximately 1 minus h squared over 2, or 1 minus a half of h squared. So all we need to do now is use these small angle approximations with this line of working here. Well, in that case here, cos h is 1 minus h squared over 2. So that's 1 minus 1, so that cancels. So all we simply get here is minus h squared over 2 times cos x. So in this case now, we obtain the limit as h tends to 0 of minus a half to minus a half h squared cos x. Okay, so that's dealt with this first part here. And now this final part here of minus sin h sin x. Well, in that case, if sin h is approximately h, then that's going to be minus h sin x. Okay, we've still got our denominator of h here. Now we're nearly there with this. All we want to do here now is simplify numerator and denominator. And in that case, if we simplify numerator and denominator here, all we're going to get here is the limit as h tends to 0 of minus a half h, so minus a half h cos x, and then minus sin x. Okay, so that's pretty much where we're up to here now. All we simply need to do now is evaluate this limit as h tends to 0. So as h tends to 0 here, in this part, minus a half h cos x, this part will tend to 0. Okay, So all that simply leaves us with then is minus sine x. Okay, and that's exactly what we wanted to show here. Okay, so that gives us f prime of x here. So if we start with f of x equals cos x, using first principles, we can show clearly that f prime of x is equal to minus sine of x there. And that concludes this Maths Made Easy video on differentiating trig functions.